Okay, maximum and minimum values. Below is the graph of y equals f of x. Now you notice it's on a particular interval, right? So this is on the interval from 2 to 11, right? Your x values go from 2 to 11. So when we look at functions, maybe we're looking at the entire domain. Maybe we're looking at a restricted domain, right? If you're using a function to model something, then there may be a reason to restrict that. Okay, so just to look on a particular interval. I'm only interested in this interval. So absolute maximum and minimum values. So the function f has an absolute maximum. In other words, it goes no higher ever. And sometimes they use global, absolute or global. So it goes no higher when x is equal to what? When x is equal to 10. And the absolute maximum value of f is 8. Okay, so that's on that interval. That is the absolute maximum. You never get any higher than that.
Wait, how is it 10? Should it be with me?
No, it shouldn't be. You should look at the same graph we are. The x value. The x value of 11 has a y value of 6. I don't think that's bigger than 8, so I'm going to go with 10, 8. The function f has an absolute minimum at x equals 2. And the absolute minimum value is 0. Now, if there were an open circle there, then it would not have an absolute minimum, right? It would, well, it's not going any lower, but it's not 0. Okay, you can get as close to 0 as you want, but you can't. So we couldn't say that it had an absolute minimum. This does, though, right? Solid dot. In general, a function f has an absolute maximum at c if f of c is what do you want to stick in here? What's going to make it the biggest? It's going to have to be the biggest. So how do we say that? We'll say greater than or equal to. So if there is a point C, right, or an x value of C, such that f of c is greater than f of x for all x in the domain, right? That's every x. That this is the absolute biggest. That's what we mean by absolute maximum. The number f of c is called the absolute maximum value of f. Okay? Sometimes they use global. A function f has an absolute minimum at c if the number, or sorry, if, and then there's a blank there. So if what? We're just going to copy this, right? If, what are we going to say? F of c is less than or equal to f of x, right? If f of c is less than or equal to f of x for all x in the domain of f, right? So in other words, it's the smallest value possible. The number f of c is called the absolute, what's it called? It is called the absolute minimum value. Absolute value of f. The extreme values of f are the absolute maximum and absolute minimum values of f. Okay, so the extremes, right? The largest and the smallest. So and then the plural of extremes is extrema. Yeah, ends with an N. Local relative maximum and minimum values. So we also have local or relative maximum minimum values. The function f has a local maximum at, so local we're talking in this vicinity, right? It's going back to the graph. Where is there a local maximum? At 4, 4, 5, and at 10, 8. Okay, so it has a local maximum when x is equal to 4 and x is equal to 10. The local maximum values are, what do we say they were, 5 and 8? the function, anybody's birthday? Oh, we'll see. The function f, besides pi, but it's not really pi's
In
birthday.
2 minutes.
Yeah, oh, that's right. Yeah. No, it's 1:59. The function f has a local or relative minimum value. Okay, so where do we have a local or relative minimum value?
3.
7. Yeah, and what's the associated value with when x is 7? 3. So it's local or relative minimum at x equals 7, and the minimum value of f at that point is 3, right? So local, we're just saying in that vicinity. So in general, a function f has a local or relative maximum at c if something when x is close to c on both sides of c. Okay, so it's going to be the same deal, right? It's going to be that f of c is greater than or equal to f of x. Okay, when x is close to c, right? And it's got to be on both sides. Okay, so in other words, as we approach it from this side, we approach it from that side, we say, yeah, okay, hey, that's the biggest point in this local area, right? So we're in this local area. The number f of c is called the local or relative maximum value of f, and then here we're just going to throw in less than or equal to, so a local or relative minimum, okay, when f of c is less than or equal to f of x. So an absolute maximum or minimum can also be a local maximum or minimum, right? So in this case, the absolute maximum is also a local maximum, right? Because it's got points around it. The absolute minimum is not a local minimum, right? Because it's only got one side, okay? This is a local minimum. It has to be in this vicinity. So, maybe endpoints are the absolute max or min, but they will never be the local max or min. Example 1. For each function, determine, kind of more state, I think, right? It's not really determining too much. Determine the absolute and local maximum and minimum values and the values of x where they occur. Okay, so the function does not have an blank value. What doesn't it have? Does not have an absolute maximum, right? Goes up forever. So it does not have an absolute maximum value. So that'll be true of any even degree function opening up, right? I mean, or same thing with minimums if it's opening down, right? If it's an even degree function polynomial, then we know that both branches go up or down, and we won't have that. The function has an absolute minimum at x equals -3, and the absolute minimum value of f is -15. The function has a local maximum at x equals 1, and that value is 10. The function f has a local minimum at x equals -3 and +3. So at x equals -3 and x equals 3, the local minimum values respectively are -15 and 5. Okay, any questions about example 1? All right, so all I do is kind of, I just go from left to right, going along the curve and just saying, hey, there's a local, an absolute and a local minimum. And, oh, there's a local max, because we reach a peak here, so in relation to the x values around it, this is the local maximum. And here's a local minimum, and there is no absolute max, and this is also an absolute minimum. So both a local and absolute. y equals g of x. The function g has an absolute maximum at x equals -1, and the absolute maximum value is 6. Function g has an absolute minimum at x equals -4, and the absolute minimum value is -4. The function g has a local maximum at x equals -1 and x equals 4. And the local maximums respectively are 6 and 3. Remember, respectively, so we got to go in the same order, right? Okay, so what were they? 6 and 3? Yeah. 6. Function g has a local minimum at x equals 1, and the local minimum value is -2. Or is it 2? 2. 2. If we do not know what the graph of a function looks like, how can we find the local max and minimum values? So let's take a look at the graph below. So here's this graph. There's some stuff going on here. So for what value of x does f have a local maximum? So what's the value of x? Or values of x? A, C, E. Congratulations, you aced that one. Yeah, it's okay. What do you expect them to? What is true of the derivative at these values of x? Yeah, so the slope is 0, right? So the value of the derivative is 0. Derivative equals 0. Well, that's true here and here, but what about here? Okay. Or it does not exist. So here we know what is true of the derivative at this point is it doesn't exist. For what values of x does f have a local minimum? B and D. Put that one to bed. Huh. And what is true of the derivative? What is true of the derivative at these values of x? 0 or does not exist. Let's go with D and E. Which leads us to Fermat's theorem, not his last theorem, because he's got a last theorem as well. But Fermat's theorem. If the function f has a local maximum or a local minimum at c, then either f prime at c is equal to 0 or f prime at c does not exist. Note that the converse of, think back to, what do you do reasoning? 20? Do you do reasoning anymore? I don't even know if we do reasoning. Note the converse of Fermat's theorem is not necessarily true. For f of x equals x cubed, f prime of x is equal to 3x squared, and f prime of x is equal to 0. This is 0 when x is 0. But at x equals 0, the function x cubed does not have a local minimum or a local maximum. Okay, and you can graph x cubed. You know what the graph of x cubed looks like, right? So it just sort of kind of flattens out, has a derivative of 0, but that's not a local minimum or local maximum. So what Fermat says is, if the derivative is 0 or does not exist, then there may be a local max or a local min.
So,
okay.
In the case of x squared, there's no local minimum, there's an absolute minimum? Is that what you're saying?
No, it's both a local and an absolute, yeah. So where I mean, you can only have one absolute max or one absolute min, right? But you can have a lot of local. If the function is continuous, then the absolute max is also a local max. Where we get max or mins that are absolute but not necessarily locals when it's endpoints. right? When we're just saying, hey, we just want to look at this interval, right? For whatever reason, you maybe graph something with respect to time, and you say, well, I don't care about negative times here, right? Like this graph would continue here. We are only interested in the interval from 0, or I'm only interested in 0 to 60 seconds. What's happening in that interval, and then describe the function in terms of its absolute and local max and mins and whatever. So a critical number of a function is a number c in the domain of f such that either f prime at c equals 0 or f prime at c does not exist. Fermat's theorem says that if the function f has a local max or local min, then it occurs at a critical number. So our job is, let's find the critical numbers. Okay. What are they? Well, they're where the derivative is equal to 0 or it does not exist. All right, then let's look at the critical numbers. We'll look at that and we'll say, now, is this an absolute or local, or is this a local or absolute maximum? So, determine the critical numbers of each function. Okay, so we've got the function y equals x cubed plus this. We are going to take the derivative. We're going to say, well, that exists everywhere, right? There are no values of x you can't put in, so we don't have to worry about that. So now we're interested in when is this equal to 0, right? So we're going to say, we could say this, so y prime exists everywhere. So there are no critical numbers by saying, hey, it doesn't exist here, right? You're trying to divide by 0, or you're trying to get the square root of a negative, and it doesn't exist there. Y prime does exist everywhere. So we'll say 3x squared plus 12x plus 9 is equal to 0. If we get to divide and factor. Okay, so the y prime is equal to 0 when x is equal to -3 or -1. Okay, so our critical numbers are -3 and -1. Okay, so critical numbers, where the derivative is 0 or where it does not exist. Okay, we don't have a problem here. It's a polynomial function. It exists everywhere. So we're just looking for the zeros. Y equals x, or sorry, absolute value of x. Well, so that function looks like this. It's x if x is greater than or equal to 0, and it's negative x, if x is less than 0. Okay, let's see, we don't need emails popping up. All right, so then what's the derivative? Well, y prime. So y prime is 1 if x is greater than or equal to 0. And y prime is -1 if x is less than 0. Which means that y prime does not exist when x is equal to 0. And so our critical number is 0. Okay, so remember, critical numbers where the derivative is 0 or it does not exist. In this case, the derivative is never 0, but it does not exist when x equals 0. Okay, so root x, which is x to the 1/2, and we can do the derivative of that. 1/2 x to the -1/2, which is 1 over 2 root x. Okay, when does that not exist? When x is equal to 0, right? So y prime does not exist. Well, it's actually a little bit more than x is equal to 0. It's really x is less than or equal to 0, right? So y prime does not exist if x is less than or equal to 0. So y prime is never 0, right? I mean, we can't put a value of x in to make that 0, but we have a critical number at 0, right? So a critical number is 0. Okay, where it doesn't exist. Where it first doesn't exist, I guess. I mean, don't really care about out there. There's nothing there, but it's 0 is the first place it doesn't exist. Determine the local maximum and minimum values of y equals x cubed plus 6x squared plus 9x plus 2 and sketch the graph of y equals f of x. For that, okay. So this is actually example 2a, right? We did that. So we know that y prime was 3x squared plus 12x plus 9. So that's 3, and what do we say? X plus 3, x plus 1. What's the value? So let's do our little chart then, right? Because we want to say, well, where are the intervals of increase and decrease, right? Where is it increasing, where is it decreasing? Because we need to know that in order to help us sketch the graph. And then what else? Well, then we're going to look at the critical numbers, because the critical numbers would tell us where we reach a maximum or minimum, right? Where the local maxes and mins are. So we make a little table, right? And we say, okay, so your critical numbers are, what were our critical numbers? Were -3 and -1. So we have intervals. So x is less than -3, between -3 and -1, and greater than -1, right? So we have 3 intervals. We split the number line into these 3 intervals. I'm not going to worry about the factor of 3, right? I mean, it's always positive. It's not going to affect anything, right? That's just always a 3. Now, if that were a -3, then I would worry about it, right? Because that means that it would always be negative, and that would affect what's going on there. So for the 3 itself, okay, I'm not worried about that. If it were a -3, I would put it in here because for all of these intervals, it would be negative, right? And that would affect. So here we're looking at f prime of x, and here we're looking at the function f. So when x is less than -3, take -5, right? This will be negative. This will be negative. F prime of x will be positive. Just multiplying the two together. And f of x, then, if that's positive, is increasing. So on the interval from -infinity to -3, it's increasing, going up, right? So it's sort of point up. From -3 to -1, so take something like -2. Well, -2 plus 3 is going to be positive. -2 plus 1, this guy is going to be negative. F prime of x is the product of a positive and a negative, so this is decreasing on the interval from -3 to -1. Okay, so it's going down, right? We're always talking about really as we're going from left to right, right? So we're going from -3 to -1. It's decreasing. So as I go through that interval, so here I've got the thing it's going up, and then it's going down, and then what's it doing here? Greater than -1, 10. That's positive. That's positive. Their product is positive, okay? Remember, because there's no negative sign here, right? You don't just want to get rid of the negatives. Oh, it's equal to 0, get rid of the negative sign. But wait a sec. That actually counts, right? It matters when I factor it out that I keep that. So this is increasing on the interval from -1 to positive infinity. So it's doing that. So we got something that's doing this, and then it's doing this, and then it's doing this. Well, but it's not V-shaped, right? So it's kind of looks like that, right? What we got to figure out is, well, so what's, where are these and what are their values, right? I mean, we already know that. It's a cubic and it's positive, so we know this from having studied the behavior of polynomial functions. I know it does this. But now we know that I need to look at the critical numbers, at -3 and -1, right? So we are now going to look at the critical numbers. So examine the critical numbers. Oh, actually, I'll just say determine okay, so at x equals -3, then y is equal to -3 cubed plus 6 times -3 squared plus 9 times -3 plus 2. 9. Okay, so we just have to work that out. -27 plus 54 minus 27 plus 2. So these guys balance, they take each other out. And we just get 2. Right? It's as if it was designed that way to be. So what have we got? Well, we know at that point, right? So if we look at it, we know, well, you've gone from increasing to decreasing, right? So you think about your slope. I would just do it with my hands. I sit there and I stick my hands up in front and say, hey, increasing, decreasing, what is that? It's a maximum, right? If I'm going from decreasing to increasing, what's that? That's a minimum. Okay. So I always sit there when I'm doing this kind of stuff, and I just sit there with my hands and say, okay, you're going from this to this, oh, you get a maximum. Or you're going from this to this, you get a minimum. Okay. So I expect to see you sitting there on a test going, yeah, it's maximum. Right? Like, what are the slopes doing, right? That's, to me, it's just the easiest way, right? What are the slopes doing? Okay. Or you could just say, really, come on, I think I know this. I don't need to sit there with my hands and do that. So we have a local maximum -3, 2, right? Because Fermat said if there's local max or mins, they're going to occur when f prime of c is 0 or a critical number, and f prime c is 0 at -3, and we've gone from an increasing slope to a decreasing slope, so there has to be a maximum at that point. And then the other one was at x equals -1. So we plug in -1. Now we get -1 plus 6 minus 9 plus 2. And what's that give me? -10 plus 8, -2, right? -2. And what have we done here? Well, we've gone from decreasing slope to increasing slope. That's a minimum. So we have a local minimum at -1, -2. So now we can draw the graph of this thing, right? We've got enough points. And we know some stuff about it. Okay. We will extend the page then. I'll draw it in here. Okay, so there's my graph. So it's increasing as a local max at -3, 2. And
Well, it's the same,
Oh.
but it's absolute.
That's probably. Okay, what do we got? We have a -3, we've got a -1, we've got a minimum here, we've got a maximum here. Okay, minorly messed up. So -3, 2, -1, -2. Forget that little bit in there. Increasing on the interval from -infinity to -3, decreasing on the interval from -3 to -1, increasing on the interval here. There's your max, there's your min. There's a small artifact stuck in there. Now the next one, we're going to the interval. Interval. Does yours say that, or did they fix that? Yours says that? No, it fixed. I think spell checker would pick that up. Interval?
It's a word.
Interval.
Probably a word.
Yeah.
Honestly.
Yeah, invariable.
Trust.
Determine the absolute max and min values on y equals x. Okay, so we know the local maximum. We know the local minimum. So we need to just examine the endpoints, right? So all we need to do is evaluate the function at the endpoints. Okay? So we have local max and mins. So we're now left to just look at the endpoints. At this point, so an endpoint can only be an absolute max or an absolute min, right? It can't be a local. Local one requires it to have stuff on both sides, right? So you could say in that vicinity. Whereas an endpoint can only be an absolute max or min. So we're going to evaluate these two values. We'll see if we get any numbers greater than +2 or less than -2, and if we do, then those will be the absolute maxes or mins. Okay, so y is equal to 5 cubed plus 6 times 5 squared plus 9 times 5 plus 2. It's 125 plus,
Yeah, it's a -5.
oh, -5. Well, that changes a lot of things. So that's -125. 5 squared is 25, 6 times 20 is 120, 6 times 5 is 30, so that's 150. So plus 150, minus 45, plus 2. So what do we got? Positive 25, negative 20, negative 18. So we got the point -5, negative 18. Is that lower than -2? Yes, it is. So this is an absolute minimum, right? Okay, so absolute minimum. Okay, the other point we want is 0. So I'm just going to say when x equals 0, what's y equal to? 2. All right, that's easy. Doesn't require much substitution. And so is that an absolute maximum? Yeah, it is. Okay, so it's an absolute maximum. Okay, it actually has the same value as the local maximum, but it is an absolute maximum.
Would they both what would make it different? Like if they both have the same y value, why would one be considered the absolute max? That's like the f of c.
It's still f of c is greater than f of x at that point. So it's the largest value, but it's an absolute position. doesn't drop off after that, and it's equal to, so it's still a maximum, right? We can't, well, you're more of a maximum because you're a local. No, you both have the same value.
Especially the two maximums, and neither one was an endpoint. You call them both absolute maximums.
Yeah. Okay, so what do you got? We got the point -5, -18. We've got the point -3, -3, 2. We've got the point -1, -2, and we've got the point 0, 2. Okay, so we're gonna go like that. So it didn't actually ask us to sketch it, but that's the diagram of it. Not, obviously not to scale. And that's a -18. Okay, so you don't need to draw this out, right? You can find, what can I have? I can let you know where maximums and minimums occur and what kind they are. So, procedure. Procedure finding the absolute max and min values of A on a continuous function on a closed interval. Notice we have to include A and B, right? We can't do, A, B round. It's got to include A and B. So find the values of F at the critical numbers of F prime. So your first step really is find F prime. Figure out the critical numbers, so where F prime is 0 or where it does not exist. Find the values of F at the endpoints. So you've got to do F of A and F of B. The largest of the values from steps 1 and 2 is the absolute maximum value. The smallest of these is the absolute minimum values. And then any local values will occur at critical numbers, right? So the endpoints can only be absolute. Determine the local and absolute maximum minimum values of y is equal to x to the 2/3 times 5 plus x on the interval. Again, at least it's consistent. Probably. There are more copy-paste errors made in the world than anything else. Right? Because people never read stuff over and they just take the thing that's wrong and we'll just copy-paste. On the interval, -5 to 1. So you have two choices, right? You can use the product rule, or you can actually just kind of multiply this in, which is probably actually the easier thing to do. Because then we just have a derivative of a sum, which is just the two individual things, instead of having to do this times the derivative of that. But, whatever you like. Okay, so what are we going to do? Well, we're going to find y prime. So y is equal to, let's do this, 5x to the 2/3 plus x to the 5/3, right? We're going to multiply the x to the 2/3 through the brackets, okay, using the distributive law. Get 5x to the 2/3 plus x to the 5/3. We're going to take the derivative of that. So that'll be 10/3 x to the -1/3 plus 5/3 x to the -2/3. Okay, so we should take out a common factor.
I thought it was -2 x to the -2.
You're right. Positive 2/3.
Actually, just a guy singing.
Good. Just keeping you honest, right? Okay, so our common factor will be 5/3, and then the lowest power, which is x to the -1/3, giving me 2 plus x to the 1/3. No, just x, right? Okay, and then we can write that as 5 times 2 plus x over 3 cube root x. Okay, so we need zeros and we need critical numbers. So where doesn't y prime exist? Yeah, so x can't be 0, right? Y prime does not exist when x is equal to 0, and y prime is 0 when x is what's going to make that 0? Negative 2, right? It's going to just, the value of x that makes the denominator 0. So our critical numbers are 0 and negative 2. Okay, so critical numbers. Okay, so we are going to. So we're going to go look at the intervals. So make a little chart here. We got an interval. We're splitting the number line up into, we've got two values there, negative 2 and 0. So we've got x less than negative 2. We've got x between negative 2 and 0. And we've got x is greater than 0. Probably is. Yeah, I guess, eh? Yeah. Because they're like, so
We didn't get to bring cake and stuff.
you did get to, nobody did. I brought a pie, but my last class ate it all. So. I know, eh?
About one pie.
So we're now going to look at the different factors here, right? We need to examine what happens with 2 plus x and what happens with the cube root of x. Okay, and then what does that make f prime, and then what does that do for f? Well, they're divided, right? But so if one is positive and the other is positive, I can have a positive divided by a positive, and okay. So I'm not going to worry about the 5 and the 3 because they aren't going to affect anything, right? I would worry about it if there was a negative 5, because then I would have to add another column here and just say I've got negative 5, which will be negative, 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 right? It's always going to be negative in those intervals. If it's, if they were both negatives, then they would be gone anyways, just be a positive. So keep in mind, I'm kind of shortcutting this, right? I'm not going to write in the 5 and the 3 because they're always positive, and But if one of them were negative, I would throw another column in here, write negative 5, and just go negative, 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 right? Just fill that in. I don't really have to examine it. Okay, if x is less than negative 2. Oh, sorry.
So that means that if you have a negative, would you want to stay on the bottom? Would you want to leave it on the bottom? Because it would change your graph if you brought it to the top.
No, it wouldn't. And
Like, why wouldn't it?
really, you could just bring it out front. You could just say this is the negative of this expression.
Oh.
Okay, so it doesn't matter. And so when we evaluated each of these guys, just if there was no negative there, it would just change the sign of whatever they became, right? So if there was a negative 5 up here or a negative 3 down there, one or the other, then I can really just put a negative out front. In which case I would have an extra column and just say, like negative 5, and then just say it's negative, it's negative, it's negative, right? Because then whatever these two guys do, that's going to change its sign. Okay, so I'm kind of sure I'm ignoring it, right? Really, I should have a column for 5 and just go plus, 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 and a column for 3 and go plus, plus, plus. But I'm just, hey, why bother? Too lazy. Or if you like, do this. Go 5 times 2x plus 3 and go 3 times this. It's going to make no difference, right? And then if this were a negative 5, then it would make a difference. You'd work this out and then multiply it by the negative. So you can do that too, right? You can put the 5 with that, the 3 with that, okay? And say, yeah, it's not going to make a difference. So when x is less than negative 2, like negative 1,000,000, then this will be negative because 2 minus 1,000,000 will be negative. The cube root of a negative is negative. Okay, and if x is less than negative 2, it's negative. A negative times a negative is positive. So this will be increasing on the interval from negative infinity to negative 2, right? So it's going up. It didn't leave a lot of room. It's newer. Okay, if x is between negative 2 and 0, let's take negative 1, then 2 plus negative 1 is going to be positive. It's still a negative, and the cube root of a negative is negative. A positive times a negative is negative, so this is decreasing. on the interval from -2 to 0. So at this point we know we've got increasing, and decreasing. So we're going to have a maximum when x is -2, right? Be a local maximum there. When x is greater than 0, that's positive, that's positive. That's positive, so it will be increasing on the interval from 0 to infinity. It's increasing, right? So we've got an increasing, decreasing, which says at this point, when it goes from increasing to decreasing, you're going to have a local maximum. And then we've got decreasing, increasing, which says at this point, at 0, where it's changing, where the slope is changing, then we're going to have a local minimum. Okay, so we've got that, and we've got that, and so now all we're going to do is find the 4 values, right? So we have 4 values we need to look at. The -5, the -2, the 0, and the 1. Okay, so we need f of x when x is equal to -5, -2, 0, and 1. Okay, those are our numbers. So these guys are the endpoints, and these guys are the critical numbers. Yeah, we have to work out those 4 values, right? Because we need to see, is this the absolute maximum, or is this the absolute minimum, right? What are these two guys? We know these are local. That's a local, what do we say, increasing, decreasing? That's a local max. That's a local min. The endpoints, I don't know what they are yet. I can guess. It's negative, but I'd say that's a max and that's a min. I don't know. So that's why I'm going to do it. Okay, so f of -5 is, let's extend the page one more time. So f of -5 is 5 times 2 plus -5 over 3 cube root -5.
How come you're not using the original? Yeah, that's the direct. Yeah,
Oh, yeah, I don't know. How come I'm doing Good question. See, that's why you guys are here, right? Make sure these videos are good. Otherwise, you know, you're looking back at them later. It's like, okay, so hang on. So we got -5 to the 2/3 times 5 plus -5. Oh, well, that one was easy. What's that equal to? 0. Yeah, it's like, I don't have a calculator. How am I supposed to do this? Well, this will take care of it. All right, let me leave that here. So we've got f of -2 is equal to -2 to the 2/3 times 5. I'm just going to write -2, right? 5 plus -2. So what's that equal to? A number. Yes. And that number is well, okay, let's expand this a little bit. Here, we'll go down. So this is the cube root of -2 squared times 3. Or, okay, so if I take a cube root and square it, I'm going to get a positive, right? So we could also, probably should have written it this way. Okay, so it's 3 times the cube root of 4. Right, that would have been smarter.
So it's cube root 108.
I don't know, we're just going to leave it as 3 cube root 4. But, yes, it is the cube root of 108.
That's right.
Yeah, if you want to put it together. So, here, we should do this. So we've got the point 5, 0. We've got the point -2, 3, cube root 4. Okay, what else? We need f at 0. So that's equal to 0 to the 2/3 times 5 plus 0, which is equal to, I'm guessing 0. And we've got f of 1, which is 1 to the 2/3 times 5 plus 1, which is equal to 6. Okay, so we've got the point here, 0, 0, and we've got the point here, 1, 6. Okay, we're not going to sketch this. We're just going to look at this and say, okay, what have we got? All right, is this an absolute max or an absolute min? Is there anything lower than 0? No, so and it's on the end, right? So it's an absolute minimum at 5, 0. So, oh, that negative function? Absolute so we've got an absolute minimum at negative 5, 0. Any other absolute minimums? 0, 0. It's also local. But it's also absolute. Because there's nothing lower than 0. Okay. What's bigger? Cube root of 108 or 6? 6. Because 6 is the cube root of 216. Okay. You just got to cube. Just cube the 6. Right? That's how you get that. So then we have what? Did it say absolute and local or just absolute? What's absolute? Local and absolute maximum. Okay, so we have what do we say, absolute maximum? At 1, 6. Nothing else is big, and we have a local minimum at 0, 0, right? Or actually, do we? This is the question, because the derivative doesn't exist at 0, right? So it's probably one of these, as opposed to one of those. Still be a local minimum, right? So local minimum. Yeah, because local minimums occur where the derivative is 0 or does not exist. Okay, so local minimum at 0, 0. Yay, that's it.
Wait, the local maximum. Yeah, I got 1 point.
No.
Yeah, negative 2.
We have an absolute maximum. So negative 2 and the 3 times the cube root of 4. Yes, so that would be a local maximum, right? Three cube root of 4. Okay, there we go. Huh. Oh yeah.